Okay, so we're going to talk about what organic chemistry is for a few minutes, and then we're going to start talking about a specific part of organic chemistry, the saturated hydrocarbons, okay? So first, as an introduction to organic chemistry, we have to understand that organic molecules are made of lots and lots of carbon, okay? That's like the main component of all of these organic compounds. You guys are living organisms, and all the organic molecules that make you are mostly made of carbon. Carbons and hydrogens. And then those hydrogens on the carbons might be substituted with things like oxygens or nitrogen or sulfur or the halogens. Halogens being things like fluorine, chlorine, bromine, iodine. Okay, so that's kind of what organic molecules are made up of. Okay, that's the components of them. So why are there so many organic compounds then? So if you consider why are there so many organic compounds versus things that are inorganic? So if we looked at a periodic table, let me just pull one up really quick. See if I find one. There we go. So I'm just going to copy this over to our presentation. Let's put it over here. Okay, so here's a periodic table, right? And if you consider the periodic table and you look at kind of this division right here on the periodic table, okay? All of this stuff that I'm circling right here, those are metals. All of this are nonmetals. Okay? So when you look at the periodic table, you say, oh, well, there's a whole lot of metals, and there's just very few nonmetals. And the thing about that is that when I make compounds, I need a metal and a nonmetal, or I need two nonmetals. Those are the two types of compounds we can have. Ionic, which is a metal and a nonmetal, and covalent, which are nonmetal and nonmetal. Now my line here actually isn't very descriptive because it should actually fall under hydrogen there. Hydrogen is actually a nonmetal, so it should be over here. Okay? So we should consider that as one of the nonmetals. But lithium and beryllium are definitely metals. Those are in the metal side. Okay. So when you look at this, you would say, oh, there must be a whole bunch of compounds that contain metals. And in reality, there really isn't. There's a few. There's a good number, but the number of metal and non-metal compounds that you can create is limited. It's limited to the fact that when you take a metal and a non-metal, there is only one way that those two things can come together. So for example, if I choose magnesium and I choose oxygen, there is only one combination in which magnesium and oxygen can come together. There's only one. They can form magnesium, which has 2 positive charge, oxygen, which has a 2 minus charge. They can come together into MgO. That's it. You cannot have Mg2O and you cannot have MgO2. You can't have those. These are impossibilities. So when I take a metal and a nonmetal, there's only one way that they come together. But if I take something like carbon and hydrogen, let's say, okay, carbon and hydrogen, there are so many ways that those can come together that I just don't even consider showing it in the same way as I just showed you how to put together those inorganic elements. Carbon, I could have one carbon with 4 hydrogens. I could have 2 carbons with 6 hydrogens. I could have 2 carbons with 4 hydrogens. I could have 2 carbons with 1 hydrogen. And I could keep adding onto this carbon and another carbon and another carbon. The thing about carbon is you can just keep adding to it and adding to it and adding to it. And then you get these ginormous molecules, just outrageously large, right? So the thing about these nonmetals is, although there are few of them, there are lots and lots and lots and lots of ways that they can come together to form compounds. There is not only one way that they come together like the metals and the nonmetals do. Just one way with those guys. But with these nonmetals, there's an almost unlimited number of ways that you can put those together. And that's what builds us. It's those nonmetals elements. That's what makes us. Sometimes we'll have a metal that associates with an organic compound, just as like what we call a substrate or something that binds to that organic molecule. So for example, hemoglobin. Hemoglobin, which is the oxygen-carrying molecule in our body, right? That's an organic molecule that will coordinate an iron right into the center of it. So you have this ginormous organic molecule, and it's surrounding one little iron atom right in the middle. Okay? So yeah, sometimes you'll get some metals associated with these carbon, hydrogen, oxygen molecules. Okay? But hopefully what you're starting to notice is, why are there so many organic compounds? Because these organic molecules can be created in just an unlimited number of ways. Okay? Okay. So also, these organic compounds, they can form ring structures. So they can have structure to them. Inorganic compounds, they don't. They don't have structure to them. They just come together and then they start to build on themselves. So think of a salt crystal. Sodium chloride, salt. There's one sodium, one chlorine. It comes together and then it starts to build a crystal of sodium and chlorines. Okay? That's the structure of it. But when we talk about these organic compounds, we don't only talk about like crystal structures of them or things like that, how they build on one another. We talk about the actual structure of that molecule. What does the structure of that molecule look like? Because they have ring structures. They have these aromatic double bond structures. They have one ring structure built onto another ring structure, built onto another ring structure. So they have all kinds of diverse ways that they come together and form the compounds that are needed for life, right? Organic compounds are the compounds of life, the things that make us who we are, that make our skin and our hair and our eyes, everything about us, right? It's just all about this carbon and hydrogen and the structure that it forms to build this, everything about us that there is. Okay? All right. Now, if two organic compounds have the same number of carbons or the same number of elements, but their structures are different, we say that those are isomers. So, for example, if I have 4 carbons, say I have 1, 2, 3, 4 carbons here in a straight chain, okay? And on each of those carbons, you need to have 4 bonds. Carbon makes 4 bonds. That's the thing about it. that gives it so much diversity in what it can form. Okay? So here's one structure of a 4-carbon molecule, but you could also imagine that it could have a structure like this. Okay? If I counted the number of carbons, 1, 2, 3, 4, it's the same. Number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of carbons here, 1, 2, 3, 4. Number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, the molecular formula is C4H10, but they're different because their structures are different. That's what we mean by isomers. We mean they have the same molecular formula, they weigh the same, they have the same number of carbons, they have the same number of hydrogens, but structurally they're different. Okay? That's what we'll call isomers. So, other important differences between organic and inorganic compounds is the bond type. So we've already been introduced to that bond type, right? Ionic bonds versus covalent bonds. Organics have covalent bonds. They're sharing electrons. Because they're sharing electrons, they can do this in a very diverse way. Inorganic compounds have ionic bonds, meaning one of the elements is going to steal the electron from another element. They become oppositely charged, and that's what allows them to come together in an ionic compound. Okay? So there's an electron transfer there that happens with that. Okay, so the structural differences between organic and inorganic. Organic compounds are molecules. We refer to things that are covalently bonded as molecules. We don't refer to sodium chloride, which is a salt, as a molecule. We say it's a salt or a mineral. Okay? So things that are covalently bonded, those are molecules. Things that are covalently bonded are usually non-electrolytes. So, you drink your Gatorade, there's electrolytes in it. Not because there's sugar in it. Sugar's an organic compound. It's a non-electrolyte. So what in the Gatorade is an electrolyte? The salts, like potassium, sodium, chlorine, iodine, anything like that. So if you dissolve sodium chloride, that's an electrolyte. If you dissolve potassium iodide, those are electrolytes because it's a metal and a nonmetal that are being pulled apart into electrolytes. Okay? So inorganic compounds are often water soluble and dissociate into electrolytes. So these are kind of the differences between organic compounds and inorganic compounds. They have a lot of physical differences as well. If you are an ionic compound, you are going to have very, very high melting and boiling temperatures. Inorganic have high melting points. Okay? Whereas organic compounds, which are covalent compounds have much lower melting points. So a way to illustrate that is to think about sugar. If you put sugar on a pan in your house, you can melt it on your stove. Okay? No problem. It's going to melt at those temperatures of your stove, which maybe you feel is high because it's going to burn you because you're an organic compound. Okay? But salt, if you put salt on your pan in your house and try to melt it, good luck. Okay? Because it's an ionic compound. It's going to think it's in the spa. It's like, oh, this is nice and toasty and warm. But it's not going to melt. Okay? You leave sugar on your stove, it's going to start burning, right? Not salt. Sodium chloride. It's just going to sit there and do nothing. Okay? Because it has an extremely higher melting and boiling temperature than does these organic sugars and things, okay? Organic compounds are often water insoluble. So think oils and fats, those are organic compounds, okay? Those are water insoluble. A lot of times organic compounds are water insoluble. You can make them water soluble with the right kinds of additions to them, okay? Inorganic compounds are often water soluble. They readily dissociate, like sodium chloride salt will dissociate in water, okay? Here's a comparison of some of these physical characteristics. So you have something that's the same molar mass, butane, which has a mass of 58. Sodium chloride has a mass of 58.5. So their masses are the same, okay? But butane is a covalent compound, C4H10. We just saw the structure of C4H10, okay? Butane is just that linear, four carbons linear. That's butane, okay? Sodium chloride, a sodium and a chlorine come together to form that interaction. Look at the boiling point. Actually, let's start with the melting point. Melting point of butane, negative 139 degrees Celsius. So if you lower the temperature to negative 139 degrees Celsius, butane will start to freeze. Okay? That's pretty darn cold, right? Above that, it's going to be a liquid. And then once you reach negative 0.5 degrees Celsius, it's going to boil into a gas. So at room temperature, butane's a gas. Okay, that's what this is saying. It's a gas. Now, look at sodium chloride. Melting point, 801 degrees Celsius. You're not going to melt sodium chloride on your stove in your house at 801 degrees Celsius, okay? It's just not going to happen. Think of sodium chloride kind of like a rock. Rocks are made of minerals and salts, okay? If you put a rock on your pan, on your stove, is it going to melt? Where do you find melted rock? In a volcano. You want to melt that sodium chloride? Throw it in a volcano, okay? Because you're not going to do it in your house on the stove. So that's what we're talking about. You want to melt rock? You got to get underneath the crust of the earth, right? Into the molten area. That's where you're going to find those temperatures, not in your house. So you see how drastic this is? Organic compounds, low melting points. Inorganic compounds, high melting temperatures. And forget about boiling it. Boiling point of sodium chloride is 1,413 degrees Celsius. Okay, so very high. All right, solubility. When you think of solubility, most of you think about like dissolves like. If something's organic, it's going to dissolve in something else that's organic because they're both non-polar. It's like non-polar stuff will dissolve non-polar stuff. Polar things will dissolve polar things. Water will dissolve the sodium chloride because sodium chloride has polarity to, in nature, to that ionic compound. Okay, it has positive and negative parts to it. Anything else that is polar will dissolve in water. But if it's non-polar, it's not going to dissolve in water. So a lot of organic compounds, which are non-polar, not all of them, but a lot of them, are going to be water insoluble. And in fact, water chemistry becomes very important to life because our bodies are made up a lot of water, right? And all the organic compounds inside of us have to interact with water. They're interacting with water somehow. If they're non-polar things, then they're going to get away from it. If they're polar, they're going to go towards it. Okay? So we're going to learn about all that kind of stuff. Okay. So let's talk now about hydrocarbons. So the word implies what it is. It's a carbon compound that has what attached to it? Hydrogens. Hydrocarbons are carbon compounds that have hydrogens attached to it. These are the most basic organic molecules you can have: carbons and hydrogens. Carbons and hydrogens are the basis for every other organic compound there is. Okay? So this is the foundation of organic chemistry, these hydrocarbons. So they contain only carbon and hydrogen. These carbon-hydrogen compounds are 100% non-polar. Which means, are they going to be soluble in water? No, absolutely not. Not soluble in water. Are they going to be soluble in other compounds that are nonpolar? Yes. So things like toluene, pentane, which also are carbon-hydrogen compounds, makes sense, right? They are also nonpolar. Yes, they will dissolve in those kinds of substances, okay? Now, if a hydrogen on a hydrocarbon has been traded out for something else, we say that it is substituted. So, for example, if you put a chlorine in place of a hydrogen, you would say that that chlorine has substituted that hydrogen, and now you have a substituted hydrocarbon. It's mostly still hydrogens and carbons, but there is a substitution on it. Okay, one of the hydrogens has been substituted. Okay? So that's what we're explaining right here. Substituted hydrocarbon is one in which one or more hydrogen atoms is replaced by another atom or group. Could be an oxygen. Could be a halogen. We can kind of think of the division of these hydrocarbons into these different groups. Hydrocarbons can be divided into aromatic compounds, which we'll discuss what those are, or aliphatic compounds. So if you ever hear the word aliphatic, basically those are organic compounds with carbons and hydrogens that are not aromatic. Okay? So the aliphatic compounds can also be subdivided into things like alkanes, cycloalkanes, alkenes, and alkynes. Okay, so an alkane is a hydrocarbon that has only single bonds. Okay, here's a good example of a cycloalkane. Single bonds, but it's a ring structure. You see how it's a 4-carbon ring structure? Okay. If it is an alkene, that means there is a double bond present. Now, whenever you add a double bond, that means 2 hydrogens are going to be removed from your structure. Okay, so if I add a double bond, now I only have 2 hydrogens on each carbon instead of 3 hydrogens on each carbon. An alkyne, that is a triple bond. If I have an alkyne, I have to remove another 2 hydrogens to accommodate the next bond. Every time you make a bond, you remove 2 hydrogens. Okay? That's what happens. So you have alkanes, single bonds. Alkenes, double bonds. Alkynes, triple bonds. Okay? And if it's a cyclical molecule, then it's cycloalkane. Now let's talk about the idea of saturation. So it's possible that you've heard of saturated and unsaturated fats. You guys familiar with that term? Okay. Well, fats are carbon, hydrogen, nonpolar molecules essentially. They have a few other things on them, but for the most part, they're just these big, long chains of carbons and hydrogens. Okay? If you do not have any double or triple bonds in that chain, it's single bonds only on the carbons, then you will have all of the hydrogens that you possibly could have, and you would term that as saturated. You would say that hydrocarbon is saturated. But if you add a double bond, which means that you must remove what? 2 hydrogens. If you add a double bond, you must remove 2 hydrogens. Then you would say that the molecule has now become unsaturated. So by saying unsaturated, what you're really saying is that there is a double or a triple bond present. Okay? So that's when you talk about saturated and unsaturated fats, that's what it means. If it's a saturated fat, then it's a straight chain hydrocarbon, saturated with hydrogens. If it's an unsaturated fat, that means there are usually it's double bonds. You don't usually find triple bonds in fats, but there are double bonds present. There might be 1 or 2 or 3, okay, depending on what fat it is. Okay. So alkenes and alkynes are unsaturated hydrocarbons, whereas alkanes are the saturated hydrocarbons. Now, whenever you look at a cyclical hydrocarbon, it might be an alkane, a cyclical alkane, but it does have 1 degree of unsaturation still, because to form that cyclical molecule, you must remove 2 hydrogens. Okay? So if this was an open chain, then I would have a hydrogen here and a hydrogen here, but no bond right there. Okay? To close the chain, I have to form that bond and remove these 2 hydrogens. So once again, there is a degree of unsaturation because I had to remove hydrogens in order to close the molecule. So this is a cyclical alkane because there's no double bonds present, which still has a degree of unsaturation. But now look at this molecule right here, benzene. It is cyclical, 1 degree of unsaturation, but then for every single double bond it has, that's another degree of unsaturation. Every degree of unsaturation is a removal of 2 hydrogens. So if I looked at this and I thought, how many degrees of unsaturation does benzene have? Well, it has 1, 2, 3 double bonds. That's 6 hydrogens removed, right? And it's closed the ring. That's a 4th degree. So, and overall, that's 8 hydrogens that had to be removed in order to form this benzene, if it was versus a straight chain saturated hydrocarbon. Okay? Both of them are. Mm-hmm. Okay? All right. Now, these are the common functional groups of organic chemistry. Okay? Each one of our chapters is going to focus on a different functional group specifically. So like we're going to have a chapter that goes over alcohols. We're going to have a chapter that goes over aldehydes and ketones. These 2 are going to be together. We're going to have one that goes over amines and amides. We're going to have one that talks about carboxylic acids. We're going to have others that talk about esters. The ether is actually going to be with the alcohol. Okay? So each of these different types of organic functional groups, we're going to spend a chapter on them. And the way the chapters work is that each chapter is designed so that first you go over the physical characteristics of these functional groups, okay, as an organic compound. And then you're going to talk about how to name them. How do we name molecules that have those functional groups on them? And then we're going to talk about what types of reactions create those types of molecules, or what types of reactions do you use these molecules in. Chapter 10, 11, 12, 13, 14, 15, that's how they're all structured. Okay? Those basic 3 things in each chapter. That's what we're looking for. Characteristics, physical characteristics, how to name types of reactions. Okay? So that's what you're going to learn for all these different functional groups throughout these next chapters, all the way to chapter 15. After chapter 15, 16, 17, 18, and 20 are organic chemistry. Then we're going to look at how not organic chemistry, biochemistry. Okay, so then we're going to look at how does the organic chemistry make the biochemistry work. Okay, so we're going to tie those together in those last chapters. All right, we're going to break